Um, uh, Thank you for the invitation. I'm Jong Kim, and I'm very happy to talk about the overarching theme of my research, which is trying to understand how the classical gravity emerges when we look at gravitation from a point of view of quantum mechanics. Yeah, so I was told to give a brief introduction of myself. So I prepared this slide, which plots my career trajectory. So one secret that I have is that when I went to college, I actually was planning to become a rocket scientist, and that's why I entered the College of Engineering. Um, so I'm now a physicist, and what happened in the team is that I went to Cheongju to serve in the military. So I served at the Air Force Academy, and then I had like some time to think about my life, think about what I really wanted to do, and that was actually when I realized that what I really wanted to do was physics. So after returning to college, I started studying physics, and that's why I have physics here. Now, I earned my master's and PhD at Seoul National University under supervision of Professor Sung Lee. So for master's, I did quantum information theoretic approaches to ADS-FD. And during my PhD, I studied scattering amplitudes and how they could be used for the physics of gravitational waves. As I was introduced, I did my first postdoc at London, Queen Mary University of London, where I joined a Center for Research in String Theory, which later became Center for Theoretical Physics. Next, I moved to Potsdam and joined Astrophysical and Cosmological Relativity group of Max Planck Institute for Gravitational Physics, which really covers all aspects of physics of gravitational waves. Currently, I'm now at Geneva, joined CERN as a postdoc. So before beginning the main talk, I'd like to give a brief introduction to the underlying question that I have for my research. So we know that quantum field theory is the language of the standard model of particle physics, which is successful, in some sense, too successful for us. And the question that I have is, why is it so successful? And at some point, we'll need to go beyond quantum field theory. How are we going to go beyond quantum field theory? And because this may sound a bit too abstract, let me just give some details about what I really mean. So when I say quantum field theory, I really mean a theory where we treat particles as point particles and describe them using local degrees of freedom, local and continuous degree of freedom, which basically means fields. And we know that the theory cannot be trusted when it makes predictions which does not make sense. For example, divergences or a breakdown of causality. And when I say going beyond quantum field theory or transcending quantum field theory, what I mean is having a UV completion where we're not talking about point-like particles, such as strings. Now, the question really lies in the context of quantum gravity, because we know that the local and continuous degrees of freedom just will not make any sense when we go to the Planck scale, where we expect that the spacetime itself has granular or erratic behavior. And of course, you may say that we already have string theory, so why should we be worried about this? And my concern here is that string theory was not really invented for quantum gravity. It was rather invented to solve the strong interactions or the physics of hadrons. So this is the original plot by Chu and Frauschke, where they plotted the spin of the hadrons against their masses. And they conjectured that they would follow a linear trajectory, which is now known as the rigid trajectory. And on the right, this is a more modern version of the same plot, which basically shows that their expectation was correct. And based on this observation, Veneziano wrote down an amplitude, now known as the Veneziano amplitude, which tries to incorporate this linear behavior in the model. And string theory was really invented to have a first principle derivation of the Veneziano amplitude rather than trying to solve gravity. And one thing that people later realized is that string theory actually has massive spin-2 particles, which can only be gravitons in this movement. This is a point that I'll come back to later. So what we know now is that string theory is a solution quantum gravity. But the real context I'm trying to ask is string theory the theory of quantum gravity? Now, this question by itself is very hard to solve, if not impossible. So the approach that I've been taking was to try to solve the inverse problem, where we try to apply quantum field theory to objects that we know cannot be point particles. When I say particle-like objects, I really mean objects that are sufficiently localized in space, such as black holes, such that if you view them from sufficiently far away, they just look like point particles. So if you view black holes from sufficiently far away so that the horizon scale is almost zero, then you will just say that the black hole acts like a point particle. Of course, quantum field theory will know that we are doing something wrong, and it will give us predictions which does not make sense. And because we actually know what the UV physics is, we actually know how to resolve the problem encountered by quantum field theory. And my approach has been trying to learn something from the process such that we can actually go beyond how, we can learn something about how to go beyond quantum field. So some examples of properties of particles that cannot be points.
Okay. Just to understand, so you are not trying to follow the top-down approach, like answering is the string theory truly the quantum gravity theory, but instead you want to study the examples where QFT cannot fully describe because it's not perfectly point-like particle, and then want to see what kind of corrections must be added to this QFT, or is this?
What must be added, and I try to learn something about how we should complete quantum field theory. Yes, yeah.
Thanks.
Right. So some properties of particles that we know that cannot be strictly point particles. I've listed two examples. One is magnetic charges, which we know that has to be attached to Dirac strings, and because it's attached to Dirac strings, it's not a point-like object. The other is spin, which can be viewed as a mild form of locality, and because spin might be something that would surprise you. Let me give you some more details about why spin cannot be a point property of a point. So the status of spin is a bit different in classical mechanics and quantum mechanics. So in classical mechanics, yes?
Please go back to the previous slide. So we have a magnetic charge, but the line, dashed line means that Dirac.
Yeah, so this line is supposed to
imply Dirac string. Like monopole solutions, right? Yeah, monopole can be,
Are you talking about Polyakov?
Yeah, for example.
Yeah, I'm really meaning here the U1 version. Yeah, so very hot Dirac strings. I mean, even if we talk about Polyakov monopoles, we are actually talking about solitons which have finite size. So the argument still holds there. Right. So in classical mechanics, there are no such thing as point particles which are spinning. So what we should understand as spinning point particles in classical mechanics is that they are really an approximation of system of point particles, which have a residual angular momentum when we approximate the system as a point. In quantum mechanics, the situation is a bit different because we know that there are elementary particles which have spin. For example, we know that electrons have spin 1/2. But the catch here is that there's an upper limit on how much spin an elementary particle can have. So for example, if a particle has spins greater than 2, which we usually call as higher spin particles, then we know that if we zoom in on the particle sufficiently close enough, then we'll start seeing its internal structures, which means that it cannot be a point particle. So that was like a brief introduction of the context of my research. And what I have been actually doing is to study classical gravity.
In the previous page,
Yes.
what is the criteria to restrict the spin of a bound to?
This one. So this really comes from the Weinberg-Witten theorem.
What is the physical condition to restrict S is less than 2?
Physical condition.
So is it impossible to construct a relativistic field theory or unitarity violation of unitarity or anything else?
It is unitarity violation.
Unitarity violation.
Yeah. Yeah. Well, for massless particles, it's a bit different because you know that there's no four limit scattering by Weinberg and Witten. For massive particles, we can write down an effective field theory, but there are going to be unitarity violations sufficiently high enough metrics. Right. So what I've been actually doing for my research was to study classical gravity using quantum mechanics, or classical gravity of spinning black holes. Black holes in quotes because I'm removing the physics of horizons when I'm describing black holes. And what I've been really doing is to study spin effects in the gravitational two-body problem using quantum field theory techniques. And you may ask, how is this related to quantum gravity? One argument that I'll make here is that if you really want to understand the true quantum nature of gravity, then we should first understand how to separate out the classical contributions when we approach gravity from quantum mechanics. Anyway, the specific topics that I've been working on was classical general relativity, perturbative classical general relativity using quantum field theory techniques. More recently, I've been interested in how spin dynamics were summed in quantum field theory using Kurzweil lines. And since I've talked about quantum gravity, I also worked on studying quantum corrections to general relativity, which I looked at quantum lens steering effect and scattering amplitudes. So what is gravity? So if you ask this question to a relativist, you'll get an answer that it's a dynamics of spacetime, which curves, bends, wiggles by interacting with matter. So this is a representation of that. But if you ask the same question to a particle physicist, then you'll get something that's completely different. So it's just an exchange of massive spin-two particles, which are also known as gravitons. And one of the facts known about gravitons is that in the far IR, the unique theory of gravitons has to be general relativity, which means string theory because it has massive spin-two particles, and is consistent theory of is consistent quantum theory. It is a consistent UV completion of general relativity. And this Einstein-Hilbert action, yes. Yes, it's known that if you have massive spin-two particles or gravitons, then it must be general relativity. The leading term must be general relativity in EFG approach.
Once you are ultraviolet, the correlation with infrared is unique. But
Yes.
It's not true the opposite.
Yeah, not true. Yeah.
So in other words, there are many quantum giving the same infrared.
Yes.
Okay.
Yes.
So
So what I've been actually doing for my calculations is that I treated black holes, spinning black holes, as spinning point particles, elementary particles, which interact gravitationally by exchanging gravitons. And because this is an effective field theory approach to general relativity, you can make effective field theory predictions about quantum corrections to classical gravity, which does not depend on the UV completion of general relativity. This was argued by Donahue almost 3 decades ago. So there are several approaches to actually implement this in practice. One of them well, one of them is the post-Newtonian effective field theory, where you treat the sources, as sources, the gravitational field, as static sources. This is one of the things that I've worked on. And there are other approaches where you actually treat the massive sources at dynamical. So they get kicked, they accelerate by interacting with gravitational fields. So there are scattering amplitude methods, and also there's the worldwide field theory method, which I've both worked on.
Question. So if you want to treat these black holes as elementary particle, you're saying you're trying to describe, for example, a single black hole as a single particle, like
particle interacting. Yeah, so 2-2 scattering, for example.
but then in QFT we use field to describe like multiple particles, right? Using second quantization. So I'm wondering what you mean by, so like I want to understand how you describe like single elementary particle in QFT.
Right. So in the EFT methods, you treat them as like world lines. The massive particles are treated as world lines, and you're integrating out the gravitational. That's the approach there. In scattering amplitudes, you don't really start from a second quantized field theory, but you build up the amplitude that corresponds to the scattering, because we know from quantum field theory that they have to satisfy certain rules, such as unitarity and Poincare invariance and these things. So you sort of bootstrap the amplitudes, and then you can treat the massive particles as the elementary particles here. In worldwide QFT, the massive particles are treated as world lines, similar to the post-Newtonian effective field theory.
Basically, a black hole is somewhere ensemble without point particles. So we should invoke some limitations or our theory to treat a black hole as point particles. So if we perform this kind of calculation, then does it give a quantum correction to Einstein-Hilbert or something?
You can compute quantum corrections coming from the Einstein-Hilbert action. You can compute the quantum corrections coming from the Einstein-Hilbert action, because Einstein-Hilbert action gives you the spectrum of gravitons and how they interact.
The candidates for the quantum correction to the Einstein-Hilbert action is well known. It can be
Yes. But we are doing an EFT approach, and when you're interested in the classical limit, then these like R³ and R⁴ corrections that would appear from the loop expansions of gravitons will not appear in the classical limit. Well, you can add them if you want the quantum corrections, but one remark that I have to make here is that contrary to the misconceptions or the widely held belief that loop expansion is the quantum expansion or expansion in H bar, this expectation is not actually true. And I'll show you soon that there's examples of loop calculations which gives you a classical contribution. And because of the subtlety in taking the classical limit, people have been looking into the log of the S matrix, which makes approaching the classical limit simpler. And because what we realize is that there are several uses of the iconal, and one of them referring to the log of the S matrix is not really what people used to call the iconal. So we decided to give it a new name and call it the magnesium. And this has been one of my more recent focuses as well. And the field actually grew because since the detection of gravitational waves by LIGO, our experimental colleagues needed better and accurate waveforms for detecting gravitational waves. And this was one of my main research focus when I was doing my postdoc at Max Planck Institute. So I told you that not all loop corrections are quantum effects. So here's an example of a calculation where if you do a one loop calculation and you get something classical. So this computation was done by Donahue and Holstein. I think it was early 2000s. And the thing they looked at was the one loop stress tensor form factor in scalar PID. So this is what they computed. So you have one particles. And the types of Feynman diagrams that you draw are diagrams where you have two photon exchange. So this is one of the examples. Now, if you do the calculation, go to the bright frame and Fourier transform to position space, this is what you get. And after restoring powers of H bar, this is what you realize. There are terms that doesn't have H bar in it. And upon further inspection, you can recognize that this is nothing but the stress tensor of a classical electromagnetic field that has been generated by a point charge, which shows that even if you do a one loop calculation, you get something classical. And one remark that I make here is that this calculation done for scalar charge, which is non-spinning, can actually be extended to spinning point particles. And one of the projects that I worked on as a PhD student was to show that this can be extended to orderly spin, which reproduces the electromagnetic field's stress tensor to orderly spin in a Kerr-Newman background.
Also a question. So does it mean that if we do this kind of calculation in QT and try to compute it order by order, and then let's say I just ignore all loop orders, like one loop, two loop.
This is one loop calculation.
Yeah.
So,
but in principle, if I completely decided to ignore all loop contribution to that stress tensor,
yes,
value, then you're not just losing quantum pressures, but you're also
you only reproduce this part.
Yeah. So in some sense, if I decide to ignore loop contribution, it's not just losing quantum information, you also lose a part of classical information.
Yes, you basically lose this part. Yeah. Here. Yeah, right. So, right. So, if you have a Kerr-Newman black hole spacetime, the limit I'm actually taking is where you send G to 0, so that you have a spinning black hole, but it only generates the electromagnetic field. And there you can expand the stress energy tensor coming from the classical electromagnetic field in terms of the spins, because depending at each order in spin, so the electromagnetic field stress tensor will have dependence in spin, because it's not going to be just linear order in spin. It has all order in spin information. And this is what I mean. So you can do the calculations to compute all and spin information about the stress energy tensor of electromagnetic fields. Yeah, but the field itself has an order and spin dependence on the Kerr-Newman black hole.
So in that frame, so you put in physical information and count. Curious, what's the
Okay, so when you have a Kerr-Newman black hole, it'll generate an electromagnetic field. Yeah, and the electromagnetic field generated by the Kerr-Newman black hole will not just be like a monopole field, which is like 1/r, not just include this the one of our square field, which is linear in spin, because it's like a dipole, but it will have all orders in spin or all order multiple expansion in 1/r. Yeah, expansion of the multiple. Yeah.
In first case, I'm equal. And common space, when you want the
Right. So in principle, what the limit we are taking is the G Newton going to 0 limit. So in this, yeah. Right. So I've mostly worked on perturbative general relativity. So let me explain a few terminologies about perturbative GR. So there are mainly two approaches to approaching perturbative general relativity using quantum field theory methods. So one is the post-Newtonian, and the other is the post-Minkowskian expansion. So the post-Newtonian expansion is something that started with Einstein, where you treat Newtonian gravity as your free theory, and then you start adding relativity corrections. So velocity corrections from special relativity and nonlinearity corrections from general relativity. So it has two expansion parameters. One is Newton's constant g, and the other is velocity v squared. In practice, you get two small numbers, gm over r and p squared over m squared as your small expansion parameters. And if you have spins, then the spin divided by mass times r, that's also considered as a small expansion parameter. And the post-Newtonian expansion is more relevant for bound motion, where you have the virial theorem that tells you that gm over r and v squared has roughly the same order. So when you're doing a post-Newtonian expansion, you count both as same order in the PN expansion. The relevant quantum field theory based method for this approach is the post-Newtonian effective field theory, which I've worked on. The other is the post-Minkowskian expansion, which I believe started from Westphal in around 1980s. And here you treat special relativity as your free theory, and you start adding corrections from general relativity. So the expansion parameter is only Newton's constant g, and you can consider the post-Minkowskian expansion as a velocity or summation of post-Newtonian expansion. Because of this, you drop the p squared over m squared in the post-Minkowskian expansion, and because you're not constraining the relative velocities of the particles, the more relevant dynamics of scattering dynamics. And the quantum field theory based methods for the post-Minkowskian expansions are scattering amplitudes and one-length field theory. There's also the post-Minkowskian effective field theory, but that one is not simply relevant. So to give a brief overview of the sectors that I worked on, I prepared the tables. So on the left, this is the table that's more relevant for post-Newtonian expansion. On the right, that's more relevant for the post-Minkowskian expansion. And as you go down the table, you're increasing one order by spin. And as you go to the right, you're increasing one order in post-Newtonian or post-Minkowskian expansion. And these are the sectors that I worked on. So some of them were state of the art when they first came out. So for example, this yellow one here, that was the computation at second post-Minkowskian order and spin cubic and quartic orders. That was new. And this green one here, which is fifth post-Newtonian spin quadratic sector, that was also new when it first appeared. And to give a reference, this is the current state of the art for the post-Minkowskian expansion, and this is the current state of the art for the post-Newtonian expansion. And you can see that although this one was worked out 5 years ago, it's still state of the art.
So F is a spin, and this is part of your relativistic correction in your previous slide. You showed that it's non-relativistic gravity.
Right. Yeah. So the spin effects can be considered as further expansions on your post-Newtonian and post-Minkowskian expansion.
And you are taking your effective field theory approach such that you allow all possible terms and then.
Yes. So for the world lines or for the massive particles, we are allowing all possible couplings to gravity. But for the gravity sector, we are only assuming Einstein-Hilbert.
And those powers in F represent
orders in the spins of each particles. Yes.
Can you just give some example of one term, like F to the?
Okay, I have them at the end of my slides. I'm not sure if I can come back.
If you have some idea.
Fast.
How do you?
Yes. Let me see. Yeah.
Wow.
Yeah, these are like the fifth order expansion. So it's rescaled and there's the spin one, spin two sector. So which looks like something like this. And this is spin one to the square sector. And there are some new terms that introduced that you can introduce because there are coupling. These are like the Wilson coefficients that corresponds to your you can add to your action. So this one is the particle moment of the spinning your spinning object. This one chain.
When you in effective field theory, you
Yeah.
need to have some symmetry principle.
Yeah.
What is the symmetry?
The symmetry principle is that you have local Lorentz invariance. So you can rotate your particle SO3 symmetry.
So it's a Vierbein formalism here.
Vierbein is needed to describe splits, yes. Because you write your effective action for the spinning particles using Vierbeins attached to the wall line of the particle.
Sorry, I'm a little bit confused that S1 and S2 are the two spins of the binary system? Or?
Yeah, so S1 is only considering spin squared of the particle one. And you have to also have spin square of the particle two, which is given by this one to exchange. And oops.
Actually, this can, so we have to think about the black hole and I don't know, neutron star, or we have to think just about particles.
Particles, well, here more relevant is black holes and neutron stars because these coefficients really.
What is the value of the spin of a black hole in this mode?
You insert your spin of your black hole in S.
It's a continuous one.
Yeah, it's not quantized. Yeah. So you're describing classical mechanics of two binary black hole system or neutron star black hole system. And for black holes, they are known to have very specific values. For example, these Wilson coefficients, this one should be fixed to 1. I think it's 1 in our normalization for black holes. But this is known to be, can go up to like 4 neutron stars. So this is a quantity that you compute from your knowledge of the UV theory. For example, if you want to compute this for neutron stars, you do a numerical relativity simulation of neutron stars with your equation state for the neutron star. And by reading off how the gravitational field falls off at infinity, you can deduce its multiple moments.
So you start from numerical calculation.
So here we're actually approaching it from an analytic calculation. You just insert these coefficients as unknowns of your particle, and which you can fit later by doing an EFT matching, where you have this UV theory that corresponds to in our simulation of neutron stars. Yeah, for black holes, these are analytically known.
So some question. Hello.
Yes, I can hear you.
Okay, so when you showed in the post-Minkowski or post-Newtonian in the series expansion, so all the terms are classical or some are quantum? How can I understand?
So, okay, let me try to.
Yeah, here, yeah.
They don't have any H-bar counting, so they are purely classical at this point.
So, but from the action or Hamiltonian, so every term in principle can be evaluated by Feynman diagram method, right?
Yes, and you can compute quantum corrections if you want, but the usual approach that people take is that people just drop Feynman diagrams that they know that there will.
Yeah, okay, that's the calculational technique.
Yes.
But the setup itself is in principle is a Feynman diagram calculation. But what
Yes.
you're saying is that all three-level Feynman diagrams, or some of them are loops, but you are saying that the loops are not quantum but classical. What is your claim?
So it depends on your approach. So if you're approaching the two-body dynamics using scattering amplitudes, then there are loop amplitudes that you have to compute, which gives you classical contributions. The status is a bit different for Wall-line quantum field theory methods, where the loop expansion actually matches the H-bar expansion.
So once we have a loop, do we have some the massless the graviton loops or photon loops or something like that, or?
If you want to compute quantum corrections, yes, but if you don't want quantum corrections, then you drop the contribution.
Okay, so in that sense, all in your results, in that sense, there is no quantum correction. It's all essentially classical.
Up to this point, yes. I'll talk about quantum corrections towards the end of my talk.
Okay, good. Okay, thanks.
I thought there was a question. No? Okay. Right. So that was part of my past research. My more current interest is trying to understand how spin dynamics resumes when you have origin spin dynamics. And the reason this is possible is because black holes are known to have very special spin structures, which is also known as the Newman-Janis shift, where if you have a black hole and if you spin it up, then the particles split into two. One moves in the imaginary spin direction, the other in the opposite direction, and they couple to self-dual part and the anti-self-dual part. So this is the statement of the Newman-Janis shift. And although this is really a statement about static solutions to general relativity, this can be actually promoted to the dynamics of point particles. So the description that I've been using was twistor wall lines, which have developed with Chun-Hee Kim and Professor Sang-Lin Ling. And one of the things that we learned from this spin resummation is that quantum field theory actually knows that you're describing something that is not a point particle by the shifts in the singularities of the two-body dynamics. So to give you an example of what we actually did, so we computed the twistor wall line dynamics when it's coupled to photons or electromagnetic fields, where the origin spin dynamics is governed by the Newman-Janis shift. Our target is what we call the Magnesian or diaconal, which is really a scalar function that actually encodes the full scattering dynamics, because from the diaconal or the Magnesian, you can actually generate all scattering observables, such as the momentum change or the spin change, as exponentiated Poisson brackets like this. Now, this is the tree-order calculation, or the first post-Lorentzian calculation, which is the equivalent of the post-Minkowski expansion. And the variable A here is what's known in the literature as the spin length vector, which has dimensions of length, which is defined by spin divided by the mass. And you can see that when we turn off the spin, there's only log B term, which has a singularity at B equals 0. But if you turn on the spin, then the singularity is moved to, depending on where your spin is.
Just to understand, maybe I'm not following because I'm not familiar with the subject. So, but when you say all orders in spin, it means you're doing some expansion with respect to this S, right?
Yes. So the expansion parameter is A over B, and you're resumming all A over B terms.
So what is B?
B is the impact parameter.
Impact parameter.
Yeah, and A is the spin length. So it's A over B is length over length, which is a dimensionless number.
So, you said you're treating like black holes as like spinning particles.
Yes.
Then that spin, so it's not going to be just like 1/2, 1 over 3/2, something like that, right?
And here it's more like a classical spin. Yes.
So it's some classical variable describing the particle. So it's just S, and then you're saying if you compute the scattering of amplitude of such particles, it's some function of S. Then you can think about the expansion in that S, right?
Yes.
Or be more precise, like S A over B, as you said.
Yes.
And then this is to fully resum the expression with respect to that parameter, but regarding the post-Lorentzian expression, it's just one PL level.
Yes. So it only has alpha or Q1, Q2. Right.
So this is but result, but you should have some starting Lagrangian with this borderline Lagrangian with F. Do you have a slide for that?
I don't think I've completed the slide for it. Yes. I cannot write it on the board, but I don't think it will actually be helpful. So right. So because you're using twistor variables, there are new. These are fundamental twistor variable, and you're coupling them to Q plus where that variable is defined by the incidence relations satisfied by I think it's this relation, incidence relation of the twistor variables. So I don't think this is much of a help at this point.
Where is F, your spin?
The spin is actually included in this set. So Z is like a position variable, but it's minus I. So it's included here. So that is like the Newman-Janis shifted position variable for your particle.
It has fixed spin one, basically.
So A here is fixed to be, it's spin, but because you're not restricting your particle to have a spin one, it's really a classical variable at this point. So you can do an expansion to all resistance A because it's not a quantum variable. Yeah. So although this looks like a quantum variable, it's actually describing a classical point particle. Classical spinning particle.
So spin should be represented by some skew-symmetric tensor rather than vector.
Right. So this relies on the fact that twistor variables are defined using a four-dimensional spinor variables. So in 4 dimensions, we can use the Pauli-Lubansky vector to define spin, and this is related to the Pauli-Lubansky vector.
So maybe I can ask a following question. So of course, I'm not familiar with this twistor variables, but in some suitable rewriting, can I just map this Lagrangian to the typical Lagrangian, like the kinetic term for relativistic particle and the coupling term like QA and like
you can do an expansion, yes. I'm not entirely sure about the kinetic. So this term will contain kinetic terms.
Yeah.
And I'm not entirely sure about the kinetic term.
It looks like, you know, the DS term and then QA.
Right. So you can expand this in terms of A, which gives you an interaction term in terms of spin expansion. The kinetic terms, I think direct mapping is a bit hard, but what we did was to show that the Poisson brackets or the Dirac brackets that's satisfied by the variables are actually equivalent. So you're actually describing the same dynamics. Yeah.
What is epsilon?
Epsilon is the epsilon tensor. So epsilon mu nu alpha beta, b mu, v1 nu, v2
function.
Yeah.
Where is the information about curved spacetime in the world line X?
Here we are coupling electromagnetism.
Whiteboard.
Here. So we are really writing this for the flat space, since we are only coupling to electromagnetism, Maxwell field. Yeah. So there is a way to generalize this to curved space. It's, I'd say, still under development because it's a bit tricky to generalize the twistor variables to curved space, because the position variable is defined by this incidence relations, but whether this incidence relation makes sense in curved space is a bit hard to say. So there's a way to generalize this action, but it's still under development. Yeah.
And it should be charged object, charged particle.
Yes. So,
But there are charged neutral spinning object in black hole and how black hole and.
right. So this was really a toy model for studying spin summation in gravity. So because we have electromagnetism, and electromagnetism shares many features with general relativity, we wanted to see how the spin summation happens in electrodynamics first before going to gravity.
So we have the Poisson bracket, and which is defined in the same like manifold, so which is the phase space. Then where are the phase space variable of the variable chi?
Right. So I didn't write it here, but right. So Z has this X variables and A variables. So X variable is the position variable, A is the spin variable, and lambda bar becomes the momentum variable, P mu. So the brackets, fundamental brackets are XP equals to delta or beta, and A is epsilon PA, something like this. I think I'm missing a factor of mass, but
It's something like the Pauli-Lubezki method.
yeah, this is the Pauli-Lubezki method. Yeah. So A mu is just n divided by the mass. Yes.
So the Poisson bracket is defined based on the space-time variable, not from the twistor variables, right?
So this is really derived from the twistor variables.
Are they equivalent? Sorry, are they equivalent?
Well, you're deriving the Poisson brackets from the relation satisfied by the So these are like composite variables. This is the fundamental variable. And it's because we decided that it's easier to describe using composite variables rather than fundamental variables. These are the fundamental Poisson bracket relations that we're using.
What is gamma? Gamma.
Gamma, I didn't include it. So gamma is V1W2. V is the momentum divided by the mass. Yeah. I think there's a minus sign because I'm using mostly positive signature here. Yes. Okay, so that was for the tree result. Something more interesting happens when you go to one loop. So this is what we computed for one loop or second force Lorentzian Magnesian. And it's actually a double infinite sum of hypergeometric functions. So you can see that there are Gegenbauer functions and hypergeometric functions are somewhere. Hypergeometric functions. Actually, you have the second term that you have to add to your double infinite sum. But one thing that amazed me, or something that I thought cannot be true, is that it actually simplifies dramatically when you go to special kinematics. So one configuration is the so-called aligned spin configuration, where you're aligning the direction of the spins with respect to the orbital angular momentum of your system. And the double infinite sum, which is a horrible expression, actually collapses down to this simple single line expression, where now you can see that the singularity which used to be at b squared equals to 0 is now moved to b squared equals to a squared, which means that the quantum field theory calculation actually knows that the spinning particles have finite size associated with the spin. The gamma variable is defined here. Another configuration where this simplification happens is what we call the axial scattering, where instead of orbital angular momentum, you're now aligning along the direction of the impact parameter. And now you have Elliott intervals, it's like here. And a special thing about this configuration is that you now have a logarithmic singularity at d squared equals to minus a squared, which is on physical region, but still it's intriguing that the system actually knows that there has to be some singularity associated with the finite size of the black holes. So far, I've mostly talked about classical mechanics, so let me talk about the work I did on quantum corrections to classical.
So related to your previous page explanation, so the two spinning objects interaction, is it purely by gravitation?
Here, it's only through electromagnetism. So there's only Q1, Q2 dependence here. So
okay.
they are exchanging.
Okay, but both are charged or neutral?
They are
charged the Q1 and the Q2. And spinning.
Yeah. So Q1 is the particle 1's charge. Q2 is the particle 2's charge.
So are they black hole, or you are talking about the fundamental particle? I'm a little bit confused.
So they are formally called root Kerr particles because they are like a single copy of Kerr black holes. But what they actually are is you can consider them as Kerr-Newman black holes where you send G Newton to 0. So they have the same multiple moments of Kerr-Newman black holes, electromagnetic multiple moments of Kerr-Newman black holes.
I see. So in that limit, the Kerr-Newman black hole size is going to 0.
The horizon would go to 0, yes.
Yeah, go to 0. So essentially, we may say the black hole is like getting to the point-like limit, point particle-like limit.
Yeah.
Okay, so I understood. Okay, thank you.
So in this calculation, gravity is negligible.
We're assuming that the exchange is only in photons. Yeah, because gravity is hard.
Not space, no gravity, just
but just photons. Yeah. So this was like a toy example for exploring gravity. Yeah.
So about 10 minutes left. So please manage your time.
All right. Right. So, okay. I'm not sure if I have enough time, but right. So what I computed was the quantum corrections to lens layering effect. What we actually looked at is what's known as the gravity rotation, where you have a spinning black hole. Because of the frame dragging field, you have the polarization getting rotated by the frame dragging field. There are several ways to compute this. One way is to take the geometric optics and approximate this trajectory as null geodesic and compute the rotation angle using parallel transport. And the other is to use quantum field theory amplitude, which does not have any reference to geodesics at all. And because in quantum field theory calculations, you're using quantum mechanics, you can actually compute quantum corrections to this effect, which just relies on the fact that you have massless gravitons in your spectrum. So, and because if you have like UV completions of Einstein-Hilbert action, there'll be derivative corrections, which have a faster fall off. So these corrections should be, this computation should be reproduced by any UV completion general theory. Right, so this is the amplitude that you're computing. So I'm computing using the cuts where we have two gravitons exchanged between the black hole, spinning black hole, and the massless particle, which are photons and gravitons. This is what you get as the computation. So I've written here in terms of the impact parameter B, but the way I prefer to write this example, this calculation is using the leading order deflection angle, 4gm over B. So this is what you get. Now, one thing that you'll recognize is that the classical part is universal. So photons and gravitons rotate the same angle. And it actually matches the geodesic computations I've mentioned, which was done by Ishihara et al. Oops. The interesting thing is the quantum corrections, which are different when you're scattering photons and gravitons, which means either they have they move on different trajectories when you're including quantum corrections, or they're experiencing different frame diagram rates. If you have quantum corrections, which is not something that we would naively expect from classical general relativity, which I'll explain in a bit
Can you
later.
remind me of what alpha is? Sorry, I missed it.
Alpha is the rotation angle. Yeah, the rotation angle of the polarizations.
So this independence start showing up at some quantum correction.
So this one is the quantum corrections. So probably this is better. It has H bar. This one is the classical part, which doesn't have H bar.
Difference between photons and gravitons are not captured at the leading order. As
Yes,
well, no, but
at the
not-
classical level, they don't differ, but the quantum level, they differ. Yes. So when you do the calculations using general relativity, you describe the waves as geodesics because you're using geometric optics, and you just integrate over the trajectory, the parallel transport over the trajectory. That's how you compute the rotation angle. And because you're describing photons and gravitons in the same way, because these two just gets determined by the background spacetime that you're computing with. This means they will have the same rotation angle, which we can say as the equivalence principle applied to Faraday rotation. And we saw that quantum trajectories for when we have quantum corrections, they are actually different. One thing that you may ask is, because these are waves, there are going to be wave optics corrections, and are they going to save the equivalence principle? Well, it is a reasonable thought because we know that the tidal effects are not constrained by the equivalence principle. But if they are indeed present, then I'd argue that they have to be related to the wave packet size or the wavelength scale, because the wave packets have the scale of the wavelengths. But we didn't see any wavelength dependence in the results as of some here. So I think this scenario is likely. And if you're familiar with the scattering amplitudes literature, this result might not surprise you because it has been known. So this computation was done by Donahue and Van Hoff in 2014, where they show that the quantum deflection angle when you have massive massless scattering actually depends on the spin of the massless particle. So the C eta coefficient here is different for scalars and photons. And also in the S-matrix approach to gravity, the equivalence principle is something that's derived from the property of the S-matrix, and not something that you put in as the property of gravity. So in this sense, breakdown of the equivalence principle breakdown is something that might not be too surprising. Then, of course, we can ask, is this something that can actually be measured? So I think that, so I think what we should ask is whether this computation that shows that the quantum corrections to the Faraday rotation angle is different, is this something that can actually be measured in experiments? Because there are arguments, recent arguments, that the quantum deflection angle computed by Donahue and Van Hoff is not something that you can resolve in experiments. And this comes back to why I prefer to write the rotation angle using the deflection angle. Because when we actually think about the experiments, then the impact parameter is not something that you actually measure in as an experimentalist. It is something that you infer from the deflection angle. So, but the rotation angle and the deflection angle are something that you can directly measure as an asymptotic observer. So I think this relation is much more robust and can be tested. So one of the future works that I'm thinking about is actually trying to understand if this difference of the rotation angle is something that you can resolve in experiments.
So when you're saying resolvable, what does it mean? Detectable?
Yeah. So you just, when you do an experiment, there's always a scale where you cannot go beyond, because you have the resolving power for your experiment. Right, so I'm almost at my time. So some of the future directions that I've been thinking about is because I'm been recently studying this Magnusian or the log matrix. I've been thinking whether this could be useful for regulating ion divergences when you do quantum field theory calculations. And one of the things that I'm more interested in now is can we define new observables based on the Magnusian? For example, the multi-particle generalization of the time delay. The reason I'm interested in this direction is because Malasina and Sibadov showed some time ago that when you have R-cube corrections to Einstein and Hilbert gravity, then it has to be completed into a stringy spectrum because there is a causality constraint coming from the time delay computed for 2-to-2 scattering of gravitons. One of the other directions that I've been thinking about is the dynamics of Taub-Nut charges or magnetic version of mass. So they are similar to gravitational version of magnetic monopoles, and their dynamics is really known through scattering amplitudes. And one of the reasons I think this would be an interesting topic is because our colleagues at gravitational wave detectors are doing tests of GR, and they're doing parametric tests where they look for deviations from post-Newtonian expansion of the waveforms. And so far, there are no known physical scenarios where you can have 0.5 pn corrections. But I think with Taub-Nut charges or magnetic mass, you can actually have 0.5 pn corrections, which is still under investigation at this point. And last but not least, so I've started the study of spin summation because one of the things known about the waveform models used for data analysis in LIGO Virgo Capra is that the waveform models degrade substantially for a high spin regime where you have fast spinning black holes. And this is expected to be the limiting factor for future gravitational wave detectors. So I'm hoping that the things that we learned from spin summation, from quantum field theory methods, will actually be helpful in improving the waveform models used for data analysis. So that was what I prepared for today, and thank you.
Thank you for the nice talk. So it's now Q&A session, so please feel free to ask your questions.
Or what is the physical consequence of violation of the equivalence principle? Actually, GR, Einstein-Hilbert action, was essentially based on the equivalence principle, as you know.
Right.
Yeah,
and that is like the relativist viewpoint. We're taking a particle physicist viewpoint that gravity is just massless spin two particles.
So you are the reason is that you are considering wave extended object. So in this sense, you said that actually violation.
Well, I'd say particles are more well defined than space-time itself.
Particles can be well defined locally. So
well, the Wigner classification doesn't really say that the particle is a local object because it only talks about momentum eigenstates. So I'm not sure if we can call particles as local objects in that sense. And because the amplitudes that we're describing are really based on the Wigner classification, where you have momentum eigenstates to define your particles. I mean, the fact that we are using quantum field theory makes them local objects, but there are some conceptual gaps, let's say it that way.
So some question about the rotation, the spinning, the spin magnitude in terms of numbers, in principle can be from order of h bar up to classical regime. In other words, a very, very huge angular momenta in terms of h bar unit, right? So your formulation can work in without any difference. Is that right?
I'm not sure I understood your question.
Okay, so you are considering the spinning particle. I'm asking about the absolute, the number of the spin. I mean, the smallest spin is h bar, let's say, right? and the discrete at the quantum level.
Yeah, right.
And while at the classical level, it's almost more or less is a huge number. We may usually say the classical rotation, right? So your formulation can work even at the quantum level of the spin, quantized level of the spin, or classical rotation. Is that right?
Well, we're doing a quantum field theory calculation where we're treating the spin as a semi-classical valued object, but nothing prevents us from extrapolating the spin A to quantum values. But I think the trouble at that point would be, can we trust the calculations?
So let me see. So what you have in mind is a huge spin, or
it's a black hole, yes.
Okay, black hole. It's a huge spin.
Yeah.
Okay. In such case, in reality, we have the maximum spin bounded by mass, right?
Yes. So
since
here
you
I'm writing
mentioned
in terms of the chi, which can only be up to 1. Yes.
right. So since you mentioned the high spinning regime at the end of the importance of the high spinning regime. So if you consider collision or some interaction between two black holes with a very extremal, with almost the extremum rotation, then there may be some instability occurring in the are there any some such signature of the instability or something? Because if there is some spin exchange, let's say some spins are transferred to the other side,
right.
it will be becoming unstable, right?
Right, but the approximation that we're doing here is that the spin back, so we're neglecting the effects of the horizon in the sense that we're treating the spins of each particles to be something that its size cannot be altered. So it's not for this calculation, but probably for this calculation here. So the expansion that we're doing is at A over B small, because that is the regime where this calculation makes sense. Because if B is of order of A, which means the horizons of the black holes would just collide.
So
then
A over B small means physically what kind of situation is it?
So you have large angular momentum compared to the spin of the particles.
Okay.
So, yeah. So L here. So A over B scales roughly as A over L.
You mean the orbital angular momentum?
Orbital angular momentum, yes. And that is when we can trust these calculations, because it's not like a head-on collision.
Okay. Okay. Thank you.
This calculation angular momentum is concerned.
At this order it is, but of course, if you go higher orders, then there would be radiation, and that would actually remove some of the energy out into like photons or gravitons. Yes.
This question maybe finishing the session. There are some. So.
Okay, so any other question?
I will go ahead. I think it's an interesting subject, yeah, asking about the spin effect on gravitation side. But somehow I think still some first principle, how spin should couple, is somehow missing. I mean, starting with this point,
right.
why spin follows minimal coupling?
Why does spin follow minimal coupling? Well, one thing that I can say is that, okay, let me see. So here the minimal coupling is slightly different from what people usually call the minimal coupling in field theories. So this is not just substituting the derivative by covariant derivatives. It also
I mean here electromagnetic minimal coupling.
Here, this coupling was motivated to reproduce this coupling. So yeah, but of course you can add like other terms to the action. One of the terms we've considered is something that looks like Q square A F bar F A. So this is like a sort of a quadruple moment that couples to the electromagnetic field at the second order. It's kind of like a tidal term. And the reason we consider this action is because the minimal coupling, you can start from the 3-point minimal coupling and then try to bootstrap your amplitudes. For example, constant amplitude where you have one incoming photon and one outgoing photon. And when you do the calculation, one of the things you realize is that as you expand in powers of spin, the amplitude makes sense up to quadratic order in spin. And beyond that, it has poles that corresponds to none of the degrees of freedom that you have. So in that sense, you can trust the amplitude up to spin squared order. And this term is needed to reproduce that bootstrap result. So that's why we consider this term. So in principle, you can add other terms. It's just we only consider this term because we were only interested in how the spin dynamics would resum when you keep the Newman-Janis shift. I'm not sure if that answers your question.
So you're saying maybe some other interactions terms describing spin and graviton or whatever in a way that this Newman-Janis shift structure is preserved. Maybe there's some other.
There might be, but so far the Newman-Janis shift seems to be a very rigid structure that it's a bit hard to.
Yeah, strong.
Yeah.
It already restricts a lot possible form of interactions.
Yes. So one of the things that I remember is that Henrik Johansson and his collaborators looked at how you could write down an effective field theory action for the spinning particle without any reference to Husserl variables. So they were looking at the more traditional way of modeling spinning objects. And they did manage to write down an effective action that reproduces this Newman-Janis shift at linear order in the coupling to gravitons. But my understanding is that this extension does not reproduce the amplitudes that you would expect from the Newman-Janis shift for multi-graviton coupling. So this Newman-Janis shift demands that for so when you are only coupling to self-dual gravitons, then your amplitude has to be the non-spinning version times the spin times the exponential of the spin times the momentum difference, and that is like one way of generalizing the Newman-Janis shift to multi-particle, multi-graviton coupling, let's say. But they failed to see that for higher orders in the coupling. But in the Twister-Waldline case, that structure is just built in by the action itself. So this is a very rigid structure, I'd say. And it's quite non-trivial that this can be extended to non-linear. Okay.
Which topics you want to collaborate with the people at the song you are so now?
Right. So with people at CERN, I've been talking about this and this. So I was trying to persuade Zibadov to get interested in this. I'm still trying.
They are collaborating there.
So Well, I'm working on the multi-particle time delay with Shota Komatsu in a slightly different context at this point. Yeah.
So, okay, so due to the time, so just less thanks to the speaker.